In this section, we're going to talk about space coordinates, and we're going to talk about what it means to have vectors in space. That is to say, in 3 dimensions. Whenever we have a coordinate system, we define an x and a y axis. However, there's nothing that prohibits us from defining a third axis, an x, a y, and a z. This is a fairly intuitive thought. After all, we live in a 3-dimensional system. Given any point, I can figure out, okay, how far from this point, how far can I go up or down? That's 1 degree of motion. How far left or right can I go? That's a 2nd degree of motion. Linear combinations thereof are still on the plane, though. So this is my x-axis and my y-axis. If I take a diagonal direction, that's still on the same plane. Really, that diagonal motion is a combination of horizontal and vertical actions. So as long as I stay on the plane, I still am limited to 2 degrees of motion. However, I can take a 3rd degree of motion by coming straight up out of the page, or poking a hole and going in through the page. But, well, I don't want to ruin my desk. So we can have a 3rd degree of motion. That's sometimes a little difficult to draw, but we're going to do our best. In order to make this a little more accessible on a 2-dimensional page, we draw with a bit of perspective. So here the idea is, okay, this is going straight up and down on this sheet of paper. This is going left and right on this sheet of paper. But this angled one, it's meant to be sort of a forced perspective, meaning, oh, look, this is actually coming out of the page toward you. Now, obviously it's not. It's also drawn on this sheet of paper. But the idea being that this one that's at an angle is meant to actually be starting from here and coming out toward you. And the reason it's slanted that way is because it's moving away from you, back toward into the page. Right? It's meant to be a 3D image by using perspective. Now, which of these is the x-axis? You say, well, couldn't it be any of them? Well, yeah, it's true. It could be any of them. But now, let's say this one's the x-axis. Which way is positive? Well, I think that way, right? Okay, now, which one's the y-axis? Well, it could be either of those. Does it matter which one? Well, no, but kind of. Because when you have the xy plane, it doesn't matter which one's x and which one's y either, does it? But we always have the horizontal one be x and the vertical one be y, because having things switch around mid-problem or between problems is a good way to get confused. So even though it doesn't actually matter which way we have things set up, there is a standard convention. Usually, this x, this is y, and this is z. This one coming in and out of the page, that's your x-axis. Your y-axis is the one going left and right, and your z-axis is the one going up and down. Here I've drawn the x, the y, and the z in the positive direction. This is the positive half of the x-axis coming toward us. Negative would be going away, retreating into the page. Positive y is moving to the right, negative is to the left, and positive z is up, and negative z is down. Right? That seems to make sense, right? At least on an intuitive level. Toward us is positive, away is negative. Right is positive, left is negative. Up is positive, and down is negative. That's at least intuitive enough because of how much we've experienced the XY coordinate system before. It's not terribly different from what we've had. One thing to note, though, is that you can have things oriented a different way. However, this is the way we do things for the most part in both math and physics. This is what's called a right-handed system. Right hand? What does that have to do with? What does a right hand have to do with this? So this is the x-axis, the y-axis, and the z-axis, and that's in a positive orientation. There's nothing really that keeps us from having, for example, this positive z being we go down, or having positive x being back into the page rather than toward us. If anything, that would make sense, wouldn't it? Positive x, it's going away from us. We're adding distance. It's going further away, plus. So why don't we define it that way? It has to do with what's called a right-handed system. This largely comes from application. Many of the coordinate systems that we see in physics, including electricity, magnetism, propagation of electrical magnetic fields, and other physical phenomena in physics, as well as biology and engineering, often have things set up in what's called this right-handed system. Okay, fine. We do things in a right-handed system because that seems to be what happens most often in nature. Okay, but what do you mean by a right-handed system? It's meant to be a mnemonic. It's meant as a way of remembering how these things are set up. Take your right hand. Okay, point. Now make a flat hand. Okay, your fingers are currently pointed in the direction of the x-axis. Okay, now bend your fingers. You see which way they're bending? That's the direction of the y-axis. The entire time you've done that, your thumb has been pointing in the direction of the z-axis. That's called a right-handed system. So in this case, if x is coming this way, if I bend my fingers, y is going this way, and my thumb is currently pointed up toward the camera. So x, y, and z. This is a nice mnemonic because even if your coordinate system changes, even if you say, oh, you know what, I want x to be pointing that way, even if it's not nicely lined up to my page, it's still going to follow the same setup. If you go into a midterm or final exam of any physics class that involves electricity and magnetism, you'll see students in their seats doing this. Why? Because in a system where a magnetic field is going this way and current is traveling this way, then the force in that system is going this way. And that same right-hand rule is used all over in different fields of physics and biology, and so we often follow suit in math because that seems to be the way systems are set up in nature. If you're going to draw a point in this system, well, then it has three components. On the xy plane, you have an x-coordinate and a y-coordinate. However, here you'd have three components. Starting at our origin, which incidentally our origin is no longer 0, 0. Our origin is now 0, 0, 0. All three coordinates are set to 0. Starting from our origin, you could go, say, for example, one step in the x direction. You can go 2 steps in the y direction. Okay, so notice that's going to be going this way. So from here, 2 steps in the y direction, that's about that far. So from here, 2 steps in the y direction is about that far. So 1 step in the x direction, 2 steps in the y direction, and then let's say 3 steps in the z direction. So let's see, 3 steps in the z direction is about that far. Like that. So this has 3 parts to it. First you move in the x direction, then the y, then the z. I moved 1 in the x direction, 2 in the y direction, and 3 in the z direction. This point would be 1, 2, 3. Positive is out, negative is in. Positive is right, negative is left, positive is up, and negative is down. Note that that means that our vectors have 3 component forms. Have 3 components in them, in their component form. So here, the vector that starts at the origin and comes up to this point directly would be the vector 1, 2, 3. So we can have a vector not just on the plane, where you start at the origin of the plane and go 1 to the right and up by 2, like this, but now you can also have a third component. Incidentally, these are not totally unrelated. This is a top-down view of this. If this is your x-axis and this is your y-axis, notice that's your x and that's your y. So z is coming up this way. So this is a top-down view. Right here I'm looking at, I'm sitting up here at the top of the z pole and I'm looking straight down. All right, so I'm looking down. This right here, this x-axis and this y-axis, are the traditional xy plane that we're used to. And here, this view is simply a top-down view. We're flying overhead. We're up here toward the z-axis, to the positive half of the z-axis. These vectors in component form are made up of 2 components. In 3 dimensions, our component forms are made up of 3 components. But if a vector does have 3 components, well, it's still a vector. It still has a distance and a direction. So how do we talk about distances and directions of something like that? Not only that, but they're still vectors, which means we still need to be able to add and subtract and scale we still need to be able to do all the things that we normally can do with vectors. So how do we do all that? Right, so let's begin with distance first. How do we measure the distance of a vector in 3 dimensions? In 2 dimensions, it seems simple enough. We're basically just using the Pythagorean theorem. We're finding the distance this way, and then this way. That forms a right triangle. And then putting those two together give us a third one. It's the Pythagorean theorem. We know that the distance in the xy plane is simply given by the Pythagorean theorem. Square root of x1 minus x2 squared plus y1 minus y2 squared. Which, if you're given a vector u, that means that it's the square root of the first component squared plus the second component squared, like that. But what does that mean for the third dimension? Well, consider an actual three-dimensional object. Well, here I have a paperclip that I've bent out of shape here. All right, so there's a distance from here up to here. All right? Okay, so how do I measure that? Well, measuring things in 3 dimensions is difficult. How do I measure a diagonal from not only diagonally this way, but also diagonally straight up and down? Well, I don't have to do it all at once. One thing I can do is, notice this is at a 90-degree angle right here. What if it wasn't a 90-degree angle? What if it was a little less? In fact, a lot less. Okay, well, I don't have to find the distance from this point to this point directly. One thing I could do is I could find the distance along the ground, along the paper, the plane. If I find the distance from here to here, and then I can figure out the distance from here straight up, hey, that's a triangle. It's a triangle that's standing up, but if I have this distance across the bottom along the floor, and then once I'm directly underneath my point, if I then figure out how to go straight up to touch my point, then that forms a right triangle also. Okay, so what does that mean? Well, first of all, I need to find the distance so that I'm directly under my point. Well, that's what I did over here, isn't it? If I'm going to be at the point 1, 2, 3, how do I figure out the distance to go from the origin to being right underneath this point right here? Oh, well, that's just from the origin to, that's 1 along the x-axis and 2 along the y-axis. Hey, that's this one right here. So in order to find the distance to get me directly underneath my point, that's just the Pythagorean theorem. That's just the magnitude of a standard vector in the xy plane. Okay, so that means my 2D distance, my distance in my two-dimensional distance, my distance in 2D. I already know that formula. That's D equals to the square root of, and again, I just wrote that right here, x1 minus x2 squared plus y1 minus y2 squared. Okay. All right, but now that's going to be one leg of this vertical standing triangle. Okay, well, what's the other leg? Well, the other leg is this one that just goes straight up. Oh, well, straight up, that only involves my z coordinate. Right? If I'm just going straight up and down, I don't have anything in my x direction or my y direction. I already took care of that by getting right underneath my point. Now I just need to go straight up. Okay, so my 3D distance is still using the Pythagorean theorem, but now it's going to be, this is one of my legs. Okay, so that's going to be the square root of, take your first leg and square it. Plus, now take your second leg and square it. Well, yeah, but my second leg is just how far I go in the x direction. Okay, so that's z1 minus z2 squared. So, that's a right triangle, straight up and down, right? So that's one leg squared plus the other leg squared. If I add those together and take the square root, that gives me the distance right across from the origin straight up. So basically, I'm using the Pythagorean theorem once to get underneath the point, and then the Pythagorean theorem again to get up to the point. All right, but, well, if I square this square root, I just get what's inside. This is positive. I know it's positive because I'm adding two squares. So squaring the square root of a positive just gives me what's inside. So that's going to be the square root of the square and the square root go away, and I'm just left with x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z3 squared. Which, hey, I basically just added another component there, didn't I? X1 minus x2, y1 minus y2, that's the same as this one, z1 minus z2. Oh, so there seems to be some justice in the mathematical world. We can add one more component, we can add one more dimension, and the distance formula simply has one extra term underneath the square root, which incidentally continues to work in 4, 5, and 6 dimensions. You say, wait, how do you draw 4, 5, or 6 dimensions? Well, we don't, but that doesn't matter. We can still compute them. There will be some times in later chapters where we're going to want to consider things in 4 or 5 dimensions. That's not to say we're going to need to draw any of those things or even visualize them, but we're going to need to compute things which thankfully seems to not take terribly, which it seems to not be terribly different from what we're used to. So here, for example, let's go ahead and find the distance from the point 1, 5, negative 2 to the point 2, negative 3, 1. Go ahead and give that a try. Here's your formula. There's distance in 3 dimensions. Pause the video, give that a try. And once you're done, go ahead and unpause and we'll go through it together. All right, so the distance is equal to the square root of, it's basically the Pythagorean theorem, but with 3 components. You take the difference in your x values, square that. Take the difference in your y values. That's minus a minus, right? Minus a minus. You take the difference in your z values. You're going to square all those and then add, all under a square root. All right, so 1 minus 2, that's negative 1. And when you square that, that's a positive 1. Plus 5 minus a minus 3, 5 plus 3 is 8. Square that is 64. And then negative 2 minus 1 is negative 3. Squared is positive 9. Put that all under a square root. So in the end, it looks like 74. Square root of 74 is the distance between those 2 points. So although geometrically it's a little harder to interpret or even represent, algebraically, hey, it's basically what we're used to. One thing to note is that in 2 dimensions, the equation of a circle comes directly from the distance formula. Right? If you have a center, h comma k, and you have a radius r, then that radius, that distance, is a constant given by the distance from any point on the outside to any point on the inside. If you call a point on the outside x comma y, well then that means x minus h, that's the distance across the x-axis. Y minus k, that's the distance across the y-axis. Okay. Okay, so then you square each of those, add them together, and then place that under a square root, the Pythagorean theorem, that gives you the distance from this point to that point. So if you square both sides, since that's a positive anyway, squaring the square root of a positive just gives you that result inside. You get x minus h squared plus y minus k squared is equal to r squared. This is the standard equation of a circle, which you learn in algebra, I believe. Maybe pre-cal, depends where you go to school. Standard equation of a circle. With center h comma k, and radius r. Well, that equation comes directly from the distance formula in 2 dimensions. Well, think about the analog in 3 dimensions. In 3 dimensions, the analog of a circle, all the points on a plane that are equidistant from a point, would be all the points in space that are equidistant to a point. That would be a sphere. So, 2 dimensions, all the points equidistant from this point on the plane form a circle. 3 dimensions, all the points equidistant from this point in space form a sphere. But, same idea. Here, we're going to use the distance formula to say, okay, well, the distance must be that r. Oh, but in our case, in 3D, this is our distance. Okay, so then that's going to be the square root of x minus, here we don't follow the tradition of h and k. We simply say x sub 0. X sub 0 means the point at the center. So here the point at the center would be x0, y0, z0. So here, this point on the outside of the sphere is the distance between that point and this point would be x minus x0 squared. Whenever you see x sub 0, it's often called x naught. X naught. It's also sometimes referred to as x sub 0. Right? As in subscript, the subscript is 0, sub 0. X naught, as in naught is just an old-fashioned word for 0. So you can say x 0, you can say x naught, or you can say x sub 0. Usually I go with x naught. That's just easier for me to say. So x minus x naught squared plus y minus y naught squared. It's also funny to keep saying why not. Why? Oh, why not? Z minus z naught squared. So that is the analog of the distance formula for 3 dimensions. And that's got to be our radius, the radius of our sphere. So by squaring both sides, again, this is the sum of squares. It's got to be positive. And if you square the square root of a positive, you just get the radicand inside. So if the standard equation of a circle is this one, then the standard equation of a sphere would look like this. X minus x naught squared plus y minus y naught squared plus z minus z naught squared is equal to r. This is the standard equation of a sphere. With center x naught, comma y naught, comma z naught, and radius r. So let's go ahead and consider an example of a sphere. Let's go ahead and find the equation of a sphere. No, so this is an example. Find the equation of a sphere that has the points -2, 4, -5 and -4, 0, 3 as endpoints of a diameter. All right, so to find the equation of a circle, we simply need its radius and its center. Okay, well, we have the 2 endpoints of a diameter. The diameter is simply from one side to the other side, going through the center. So here, one diameter would be something like this. All right. Okay, so the radius must be halfway in between, because if this diameter goes from one side to the other, the radius is right in the middle. Okay, so what we want to do is we want to find the midpoint between these two. All right, well, in a circle, the midpoint is simply the average of the x-coordinates and the y-coordinates. After all, what's the point that's halfway in between two numbers? That's their average. All right, if you have a 100 on an exam and a 90 on an exam, halfway in between, 95, that's your average. So here, we're going to find the average of our first component. We're going to find the average of our second component. And, well, now we have a third component. We didn't have that before. So what? Find the average of the third components. One of the nice things about distance is it does appear to be done component-wise. So here the midpoints, the midpoint will simply be the averages of my components. So let me add my two components together, divide by 2. Add my components together, divide by 2. And add my components together and divide by 2. Notice this right here would be exactly the way you would see it in an algebra course. Right? This would just be the basic midpoint between 2 points on a line. Well, now this is the midpoint between 2 points on a line in space. Just an extra component. All right, so that means that our center is -6 divided by 2, that's -3. 4 divided by 2 is 2. And -2 divided by 2 is -1. So there's our center. So now we need our radius. To find our radius, we can either find the distance from one of these points to our center, or we can just find the distance between those 2 points and cut it in half. It really doesn't make a difference. So here I'll just go ahead and find the distance between this point and this point. Okay. Why? Because I have to do one of them, right? Either the distance from the point up here to the middle, the distance from the point down here to the middle, or the distance between those 2 points and then cut it in half. I'm just going to pick this one because it has a 0 in there, and 0 probably means there's one less thing I have to do. So now my radius is going to be given by the distance from here to here, and in 3 dimensions, that radius is simply given by the square root of the Pythagorean theorem with one extra component. All right, let's subtract our x components, our first components, -4 minus a -3. Subtract your second component, 0 minus 2. And your third components, 3 minus a -1. All right, so that's what? -4 plus 3 is -1, squared is +1. -2 squared is +4. And double negative makes that a plus. That's 4 squared is 16. So that means that our radius is the square root of 21. So now we're just about done. We have our center, we have our radius. So now to put this in standard form, we're going to write x minus the x component of our center. Minus a minus would be plus. Squared. Plus, here we're going to take y minus the second component. Squared. Plus, we're going to take z minus our third component. Okay, well, minus a minus, that makes that +1. And that's going to equal to r squared. This is r, which means r squared must equal to the root of 21 squared, which is just 21. So this gives us our equation of our circle in standard form. Finding the equation of a circle in standard form isn't going to be something super important, although we will sometimes see this for certain examples. But here, the main thing to get out of this is how distance works in 3 dimensions, how it's very similar to distance in 2 dimensions, but how the difference is that extra component. So if we're talking about a vector in space, it becomes apparent that it's going to have a lot in common with a vector in 2 dimensions. Really, the only difference is the third component. So here, let's take a look at a theorem which pretty much highlights the similarities. All right, so theorem. Let's begin with a vector in 3 dimensions. Here we'll give it in component form as u1, u2, and u3. And v is given by a vector v1, comma, v2, comma, v3 in component form. All right, so let's let those be vectors in space. And let's have a scalar c. In that case, all the following things are true. The vector u and the vector v are equal if and only if u1 equals v1, u2 equals v2, and u3 equals v3. So in other words, 2 vectors are equal if and only if all of their components are the same. 2. The vector from the point P1, P2, P3 to the point Q1, Q2, and Q3 is given in component form as V1, V2, V3, which is found by taking the difference of the corresponding components. Note that the order does matter here. If you're going from P to Q, then the first component is given by the first component of Q minus the first component of P. Basically, a component is given by the endpoint minus the initial point, where you're going minus where you started from. Here we're going to have Q2 minus P2 and Q3 minus P3 as our third component. The third property here, this is an extension of what we see in 2 dimensions, and that's the length, the magnitude of the vector v in 3 dimensions, is given by the square root of the sums of the squares of the 3 components. Before we only had 2 components, but in 3 dimensions now we have 3 components. So that'll be v1 squared plus v2 squared plus v3 squared, and we'll take the square root of all of that. Number 4, if you take the vector v and you divide it by its magnitude, which is really the same as saying you're taking the reciprocal of its magnitude and using that as a scalar to multiply times v, that's equal to one over the magnitude of v times the components v1, v2, v3. Or, even more simply, it's given by v1 over the magnitude of v, comma v2 over the magnitude of v, comma v3 over the magnitude of v. So if you want to take a vector and find a unit vector, you'll remember from our previous section, this was a unit vector in the direction of v. You simply take the components of v and divide each one by the magnitude of v, provided that v is not the 0 vector. Because of course if it is a 0 vector, then its magnitude is 0 and all of this is undefined anyway. Vector addition is defined the way you would expect it to be. The sum of u and v is simply the sum of the components, u1 plus v1, comma u2 plus v2, comma u3 plus v3. And scalar multiplication is what you expect it to be. U times c times u is simply given by the component-wise scaling, cu1, comma cu2, comma cu3, just like that. Note that the proofs of these are, we're going to forego the proofs of these, mostly because we've already seen them. The proofs of all of these will mirror exactly the proofs that we see in the previous section on vectors in the plane. The only difference is now you have a third component, but that third component is going to behave just like the first two did. So there's nothing new to be gained by proving this with the third component, since it looks identical to the proof of the statement in vectors in two coordinates. So rather, as an example, consider the vector u in 3 dimensions to be given by 2, -3, 5. The vector v to be given by 0, 2, -4. Here, these two vectors can be added component-wise. We can say u plus v is equal to, we're going to add these two together, 2 plus 0, that's going to stay 2. Adding these together, -3 plus 2 is -1. 5 plus -4 is +1. We can scale any of these by simply multiplying each of the components by that scalar. So for example, if I want 2u, that's simply going to double each of the components in u. So that'll be 4, -6, 10. Let's say I want to find the unit vector. Let's say I want to find the unit vector in the direction of v. That's the vector that has this direction, but that has distance 1. Well, then really all you need to do is you're going to find the magnitude of v, and then you're going to divide by that magnitude into each of those components. So in fact, let's go and do that first. Let's find the magnitude, which we see is same as finding the magnitude of a vector in 2 dimensions, but with a third component. So here that'll be 0 squared plus 2 squared plus -4 squared. With 2 dimensions, it would just be that. With the third dimension, you throw in your third component. So that would be the square root of 0 plus 4 plus 16. Or in other words, it's root 20. So that means that the vector v can be divided by its magnitude. We're simply going to divide each of these components by the magnitude. So that'll be 0 over root 20, which is just 0. We're going to have 2 over root 20. And then we'll have -4 over root 20. As is often the case, we're going to rationalize these numbers here. So 0 stays 0. Here, root 20 is the same as 4, is the square root of 4 times 5. Or in other words, the square root of 4 times the square root of 5. Or in other words, it's 2 root 5. Right? Root 20 equals the square root of 4 times 5, which is root 4 times root 5, which is 2 root 5. So here, that'll give us 2 over 2 root 5, which is just 1 over root 5. Right? The 2 in that and divides the 2 in that. And then -4 over 2 root 5 gives us -2 over root 5. The 4 over 2 reduces to -2 there. And then we can rationalize that. We can multiply the top and bottom by root 5, and we get 0, comma, root 5 over 5, comma, -2 root 5 over 5, which is usually the way you see the answers written in our textbook. Okay. Finally, the last thing we want to look at here, we have one more definition to talk about, and that is what does it mean for two vectors to be parallel? We see what it means for two vectors to be equal to each other. It means all the components are equal. Right? If all the components are equal to each other, u1 equals v1, u2 equals v2, and u3 equals v3, then the vectors are equal. But if they're not equal to each other, they can still be parallel to each other. That's a definition here. Let u and v be non-zero vectors u and v are said to be parallel to each other if one is a scalar multiple of another. So if there exists some scalar c such that u is equal to the scale of v, c times v. Or in other words, if you can take one of them and multiply it by some just regular constant, some scalar, and get the other one, then those two are parallel to each other. So some examples of this. Let's say we have the vector v is equal to 3, negative 2, 4. Well then, if I have 2v, that's 6, negative 4, 8. Those two are parallel to each other. Why? Because one of them is just the scale of another one. This one is 2 times that one. It wouldn't have to be a whole number. You could say 3 fifths v. Okay, well then that would be 9 fifths, negative 6 fifths, 12 fifths. And that would be parallel to that one. Because again, one is a scaled version of the other. It doesn't have to be scaled by any whole number necessarily. It can be any number, as long as there's some scalar. You could even have a negative. I could say negative 3v. Okay, well that would be negative 9. That would be positive 6 and negative 12. And again, because this is some scalar times v, then all of these are parallel to each other. Okay? Now, you can take two vectors and determine if they are parallel to each other by simply comparing the scale between their components. What I mean by that is, okay, one thing is to say, yeah, I know that these vectors are parallel to each other because I can clearly see that I got one by scaling another one. But what if I didn't know that? What if I just had two vectors and I said, okay, are these parallel to each other? 2, negative 5, 7, negative 3, 15 halves, and negative 21 halves. Well, this way is simple enough because I know where I got these from. But here, how can I tell? Well, you can compare the scales between one and the other. Go ahead and divide these. I'm going to take the first component of the second one divided by the first component of the first one. I can do it the other way around, but let me be consistent. So I'm going to take the components of the second one divided by the components of the first one. If you do it the other way around, that's fine too. Just be consistent. All right, so let's see. Negative 3 over 2. Okay, well that's negative 3 halves, right? I can say negative 1.5 if I like. Okay. Let's try these here. 15 halves divided by negative 5. Let's see, 15 halves, positive divided by a negative is a negative. 15 divided by 5 is 3 halves. Oh, that's also negative 1.5. So it looks like if I multiply this by negative 1.5, I get that one. If I multiply this by negative 1.5, I get that one. Now, that's got to work for all three of them. If I take negative 21 halves and divide the whole thing by 7, negative over a positive is a negative. 21 divided by 7 is 3 halves. Negative 3 halves, negative 1.5. Yeah, that's fine. So it looks like here, if I take all of these and multiply them by the same number, negative 1.5, I get this one. Or in other words, this is this one scaled up by negative 1.5, negative 3 halves. So yes, these are parallel. If I take negative 3 halves times the first one, I get the second one. So yes, these are parallel. Just like that. Let's take a look at another example that's directly related to this. It's going to sound completely different, but it really is the same kind of question. Are the points 1, negative 2, 3, 2, 1, 0, and 4, 7, negative 6, are these collinear? In other words, are they on the same straight line? Is there a line that contains all three of those points. That's what it means by collinear. Here, we're going to go ahead and give these names that we don't have to keep referring to that one, and that one. We're going to say P is equal to that, Q is equal to that, and R is equal to that. So these are points P, Q, and R. All right. First of all, let me find a vector from P to Q. So let's say this is P and this is Q, right? I'm trying to find this vector here. Okay, well, I know how to find the vector between two endpoints. I take from my previous definition over here, to find a vector, I go ahead and subtract the end component minus the initial component. Okay, so that's going to be, take my end component, I'm going to end at Q, minus, I'm going to subtract away my initial component. I'm going to start at P. So Q2 minus P2 and Q3 minus P3. Okay, but we know those things, right? Q1, that's 2 minus 1. And then 1 minus a negative 2. And then 0 minus 3. It's always endpoint minus initial point. All right, so that means that this vector from here to here, from P to Q, is what? 1, 3, negative 3. Just like that. All right, so now we can find the point, we can find the vector from point P to point R. Okay? Now, these two vectors have the same starting point. So let's say R is over here. Let's say it is collinear. Well, if they have the same direction, meaning if they're parallel to each other, and they have the same point, which they do, they both start at P, then they must all be on the same straight line. But if they don't have the same direction, in other words, if they're not parallel to each other, if they're at an angle to each other, then if they start at the same point, but they're not parallel, that must mean that no, this P, this Q, the R would be somewhere over here. It would be someplace where it didn't line up with this. So what we want to do next is we want to find the vector we have from P to Q. We want to find from P to R. We want to find out, okay, is it parallel? That means it's on the same straight line. Or is it not parallel, meaning it's somewhere else? So go ahead and finish this off. Go ahead and pause the video, find the vector PR, and then see, are they parallel to each other? If they are, then everything must be collinear. If not, well, then they're not. Go ahead and pause the video, give that a try, and once you're done, go ahead and unpause and we'll go through it together. All right, so let's take a look. PR, you're going to start at R. You're going to start at P, go to R, which means your vectors are going to be given by the difference, the components of R minus the components of P. The terminal points minus your initial point. So that'll be 4 minus 1, 7 minus negative 2, and negative 6 minus 3, which gives us, what, 3, 9, and negative 9. Okay? So here we find that PQ is this vector, PR is this vector. If they're parallel, well, if they're parallel and share a point, then they must be the same line. But if they're not parallel and share a point, that means they're off at an angle. So here R would be on some other line, not on the same line. So the question is, are those parallel? Well, of course they are. Here, if I take, here I'm just going to take the components of PR, divide them by the components of PQ. 3 over 1, 9 over 3, and negative 9 over negative 3. All of those are going to give me 3. So that means that PR is simply 3 times PQ. So PR is equal to 3 times PQ. So by definition, that means they're parallel. Thus, the vectors are parallel. But if I have two vectors that are parallel and they share a point, then that must mean they're the same line. So P, Q, and R are collinear. And that makes us happy. Finally, when we talk about component form in 2 dimensions, you have something like V1, comma V2. You can also write that using standard unit vectors, I and j. You can write this as V1i plus V2j. So for example, if you have the vector in component form 5, comma 3, then in this form, where we're using the standard unit vectors, this would be 5i plus 3j. Well, in 3 dimensions, you have the same thing. If you have a vector v1, v2, and v3, that can be written as v1i plus v2j plus v3, and the third component, just to keep the pattern going, ij, the third one is typically called k. So for example, if you have the vector 1, 3, 5, that can be written as 1i plus 3j plus 5k. And although that doesn't really give us anything new, it's just a different way of writing it, a different notation, it is seen fairly often in applications. For the most part, this is seen in math and this is seen in physics. Right? They work the same way, they're just different notations. But you will occasionally see one, and other times you'll see the other. And just note that even though they're written differently, they are the same. So they share all the same properties. Some people are more comfortable with one or the other. So if you come from a physics background and you're comfortable and you're familiar with these and you're already comfortable with them, you can always turn your component forms into this form where you're using the unit standard vectors, or vice versa. If you're more comfortable with these, you can always write these in component form. They are exactly the same. And that's it. So that brings us to the end of our section. If anybody has any questions, comments, or problems, please reach out and let me know. Otherwise, I hope everyone has a nice day.